Hi everyone and welcome to a new video about noise analysis of OpAmp circuits, and this is our example number 2. In this example we will look at the inverting amplifier, and we will of course do the step-by-step the calculations, and we will verify our calculations using simulations in SPICE. So let's look at our example number 2. We have the following circuit given, which is an inverting amplifier, which has a feedback resistor R2 of 20 kilo ohms, and it has an input resistance of R1, which is 10 kilo ohms. And the op-amp here we are using is X1, which is an OPA 209. What we want is calculation of the input referred RMS noise voltage, which is given by the capital letter E sub N in, and the output referred RMS noise voltage, which is then capital letter E sub N out. So those two are unknowns. So we have the input voltage as the AC signal, we have the output here, and we have two power supplies given. So let's look at our solution step by step, and before we move on with the solutions, let's look at our OpAmp specifications for this OPA 209. The important graphs are shown here. So we have the input noise voltage spectral density on the left side, and we have the input noise current spectral density on the right side. But we also need are some parameters of the op-amp, like the open loop gain, the frequency response like the gain bandwidth product, and also the noise for specific conditions. But these are also shown in these graphs. Let's look at it for the op-amp step by step. So the DC open loop voltage gain, which is given by A sub OL, which is 132 dBs, which is also shown here, which is actually shown here. So the open loop voltage gain. The gain bandwidth product, which is a very important parameter of the op-amp, is 18 megahertz, which is actually shown here. The next one is the broadband or the white noise voltage spectral density, which is then given by the small letter E sub N BB, broadband, which is then 2.20 nanovolts per root hertz, and that is shown here. At that frequency, that means actually from that frequency and further, you will have this value. You can also see that from the graph here on the left side, that approximately at 1 kilohertz, this value of this plot will stay at approximately 2.2 nanovolts per root hertz. But before that, it has some dependency on the frequency. The same is valid for the broadband noise current spectral density, which is then given by the small letter I and sub MBB, which is then again for the current density. That is 500 femtoamps per root hertz, which is actually shown here, also in the table, again from 1 kilohertz, but it is also visible in this plot on the right side. You can see that here. So approximately at 1K, it starts to settle down. Actually starts much earlier, but it is measured at that value, and it has a value of 0.5 picoamps per root hertz, which is of course exactly as 500 femtoamps per root hertz. What we also want is the region here, which is called the 1/f noise region, which is also valid for the current noise, for the voltage noise. We have at 0.1 hertz, which is just at some frequency, but it is now taken at 0.1 hertz. We have the 1/f noise spectral density, which is given by this symbol, which has a value of 20 nanovolts per root hertz, which is actually shown here. So you can see the 0.1 hertz, it has a value of 20 nanovolts per root hertz. Now, similar, we have the 1/f noise current density, which is then also at that 0.1 hertz, again given by this symbol, and it is then 3.75 picoamps, which is then shown here in the graph. Okay, those are the specifications and some important parameters of the op-amp. So let's look at the circuit performance of this circuit. What we have are actually two resistors and an op-amp, and we have the input voltage, and we measure the output at this node, and we have power supply just to run the circuit. We have for the gain actually two gains. We have the closed loop signal gain, which is actually the gain just to amplify the signal, and we have the noise gain, which is actually the amplification for the noise itself. So for the signal gain, we know the formula for that one is the feedback resistance divided by the input resistance, of course the minus, because this is an inverting amplifier. So we have minus 20,000 over 10,000 will be minus 2. That will be the signal gain. But that is now an important thing, which is actually different than the first example. The noise gain is always taken from a non-inverting input of the op-amp. So if I have a source here, considering the source here, which is a noise source, and then of course making the input voltage source a short, so I will disable this, then I see this actually as a non-inverting amplifier. Then it will be 1 plus the feedback resistance divided by this resistance, which is going to ground. Then I have actually 1 plus to 20,000 over 10,000, which is then now 3. So the noise gain is different than the signal gain. So the magnitude of the signal gain is 2, which is of course minus 2, which has a sign, but in magnitude it is 2. But the noise gain is 3, so this is different. So that will be of course important for later on. The noise bandwidth and also the closed loop signal bandwidth will be also of course given here. So we have a signal bandwidth which is given by S bandwidth, BW. We have the noise bandwidth which is then given by NBW. The signal bandwidth is calculated from the specifications of the op-amp. We know that the gain bandwidth product was 80 megahertz, and we have noise gain, so we have the gain bandwidth product over noise gain, which is then the 6 megahertz for our signal bandwidth. That means actually the cutoff frequency for this op-amp, considering it's the first order low pass filter, will be 6 megahertz. So we have an op-amp, in this case just one op-amp, and there are no other active or reactive components. So there's no other op-amp, there is no capacitor or inductor involved, or no transistor. So we can assume, of course, that this is a first order circuit, and then the brick wall conversion factor, which is used to convert the signal bandwidth to a noise bandwidth, is 1 pi over 2, which is then 0.5 times the pi. This is a value you can of course derive, but I won't go to the details, so that is just what we use as a conversion factor. Okay, that means the following. Considering this circuit as a first order system and then having a brick wall conversion factor, the closed loop noise bandwidth for the circuit will be then given by this expression. So I just multiply the signal bandwidth by this conversion factor, I will have the noise bandwidth. So it will be pi over 2 times the 6 megahertz will be the 9.425 megahertz. That is the actual noise bandwidth we will need to use in our calculations, not the 6 megahertz. So let's look at the total noise voltage now. We have the performance, now the total noise voltage. Now the input referred RMS noise voltage again, and we have the output referred RMS noise voltage. Those two are of course the end results we need for this exercise. Now those two together, we can then calculate the output noise voltage, RMS value of that one, then using the noise gain multiplied by the input referred RMS noise voltage. So this is actually an important expression. So the input referred RMS noise voltage is then composed of 3 parts. And to understand that, let's look at the model of the circuit. So I will add in this circuit for the op-amp specifically some model parameters like the current source for the op-amp and also the voltage source as the noise sources. So we have the noise source here, current noise actually, and we have the noise source here, which is then the noise voltage source. And these will have effect, of course, on the output noise. So that's now a noiseless op-amp which has its own noise sources in the model. So the input referred RMS noise voltage is then now composed of 3 parts, which is then due to the internal op-amp noise voltage, this one. That will of course produce some output, but also has some input noise voltage. It has also the input referred RMS noise voltage due to the internal op-amp noise current. So this will also have some noise at the input, which will of course also reflect the output. So we always start with the input and then multiply that by the noise gain and then go to the output. So this will produce some input noise voltage in this condition for the circuit, and this will create also some noise voltage at the input. And these are given by these symbols. And we have the white noise produced by these two resistors, which are of course also called the broad thermal noises. So we have also the input referred RMS noise voltages due to the resistors, and which is given by this symbol, capital letter E sub N R. So we will take them together, and then using the root sum of squares, we can calculate the input referred RMS noise voltage. So the total input referred RMS noise voltage will be calculated using the root sum of squares, which is that the following: the E, capital letter E sub N, in the input referred RMS noise voltage is the square root of the square of each term, and then add them up. That means root sum of squares. Yeah, we will use this later on. But first, we need to calculate each of these elements independently and then add them up in this form. So let's look at our next step, which is then the input referred RMS noise voltage due to the internal OpAmp noise voltage sources. So which is then this one. So the input referred RMS noise voltage due to this is then again on its own composed of two parts. We already seen that in the first discussion about the plot, which has a broadband noise and also the 1/f noise. And we will need that together to come up at that complete noise voltage at the input, specifically given by this. So the E and F is calculated using the root sum of squares again, and we have then this expression for this part, which is then the broadband noise voltage squared and the 1/f noise voltage squared, and all of them are in RMS. So we have also the RMS value for our case in this part. So the broadband noise voltage then is given by this expression, which is then the RMS value of the broadband noise voltage is equal to the broadband noise voltage spectral density times the square root of the noise bandwidth. So we know already what the signal bandwidth was, which was 6 MHz. We already calculated this. And using the specification of the OpAmp, we can then go to the noise bandwidth. So we know that the signal bandwidth was 6 MHz, again using the gain bandwidth product and the noise gain, which is 3 in this example. Then we have the 9.425 MHz. And that will be, of course, substituted in this expression using 2.2 nanovolts per root hertz for the broadband noise voltage spectral density here. And you do the math, you will get approximately 6.75 microvolts RMS. So we know already the part here. Now for the 1/f noise, which is then dependent of frequency, that will be given by this expression. I won't drive this, it is a formula you can just use. Of course, there are some books and literatures that can give you the derivation, which is then here the upper cutoff frequency. It is given by the closed-loop noise bandwidth, so you can just fill in here the noise bandwidth which you have. There's a normalized frequency, normalized noise bandwidth, noise voltage, I mean, for this part, and we have also a lower cutoff frequency, which will be just a selected value. So this is the selected frequency for the normalized 1/f noise voltage. This is sometimes taking a different value, and most of the time it is 0.1 Hertz, but any value will do the job. So the normalized noise voltage, this one, is then given by this expression. So we use this from our specification, which is 20 nanovolts per root hertz. You multiply that by what you have selected as your lower cutoff, which is in this case 0.1, but you can also take another one. If you do the math here, you will get 6.325 nanovolts RMS. That will be used here in this expression for calculating the 1/f noise RMS value. So if I now do the math here, just substitute values for the noise bandwidth, 0.1 Hertz for our selected lower cutoff frequency, and also the normalized noise voltage spectral density, noise voltage, normalized noise voltage, you will have 27.10 nanovolts RMS, which is then 0.02710 microvolts RMS. And compare this one, which is then for the 1/f noise, and this is then for the broadband noise. You can see this is much larger than that one, so this will actually dominate the actual result for this part. And you can also see that when you do the RMS value for the broadband noise and also the 1/f noise, taking them together using the root sum of squares, using this formula and then substitute the values, you will see that this is actually also the end result. So you will see that the dominant part in this example is the broadband noise voltage. Okay, now let's move on with the next one, which is then the input referred noise voltage, RMS noise voltage, due to this part of the op-amp, which is then the internal noise current source. So how do we move on with that part? We calculate the equivalent resistance seen by this source and the noise current source of the op-amp in RMS value. So that is what we need. So the equivalent resistance seen by the noise current source of the op-amp, that is this. This is, if you look at this node, so between these two nodes, and I will of course make this short because I use superposition, and this is also shorted. These two resistors are in parallel form. That's actually what we have, the R1 in parallel with R2, and then this is actually the formula for calculating the equivalent resistance. The input referred RMS noise voltage due to this noise current source of the op-amp will be calculated using this formula, which is just Ohm's law. Once you know the equivalent resistance, you can multiply it by the noise current source of the op-amp, then you have the input referred RMS noise voltage, which is given by this symbol. But this is the I sub n, so the capital letter I sub n on its own is also composed of two parts. Again, the broadband noise voltage and also the 1/f noise, the broadband noise current and also the 1/f noise current. So that will be also calculated using the root sum of squares. Again, in similar form. So we need to calculate them one by one. Let's do that again in a similar form. The RMS noise current is then given by, for the broadband, is then the noise current density for the broadband part times the square root of the noise bandwidth. Now we know the signal bandwidth, again using the specifications from the op-amp, and also then using the brick wall conversion factor multiplied by the signal bandwidth, we will have again that 9.425 megahertz. You substitute the values, you get this from from this OpAmp specification, which is 500 femto amps per root hertz or 0.5 pico amps per root hertz. You multiply it by the square root of the noise bandwidth, you will get 1.535 nano amps RMS. That is this part for our broadband noise current. For 1/f noise current in RMS is again a similar expression as we did for the 1/f noise voltage. So again, the normalized current times the square of the ln in the ratio of the upper cutoff frequency over the lower cutoff frequency. Now we know that f sub h is the closed loop noise bandwidth, which is this one, and the fl is a selected value for the normalized 1/f noise current, and we will use the datasheet for that one. Now we again take 0.1 hertz, but any value will do for fl. Now the normalized noise current is then given by this expression, similar to what we had for the normalized noise voltage. You will take this 3.75 pico amps per root hertz, which is actually this one for the 1/f noise current density. You multiply by the square root of the fl, which is then taken as 0.1 hertz, and you will have 1.186 pico amp RMS. I will now substitute this in here and also the noise bandwidth and the 0.1 hertz. Then I will have this value, which is then 5.081 pico amps RMS. Now what you see here is this is the broadband noise current result, which is 1.535 nano amps RMS or 1535 pico amps RMS if you do it in pico amps, and this is just 5.081 pico amps, so it is much larger than the 1/f noise part, so this will again dominate in this case. So if I move on with the calculations for the total noise current, RMS noise current, we will calculate it using the broadband noise current, also 1/f noise current, using again the root sum of squares. So if you do the math here, you will have for the final result 1.535 nanoamps RMS. Again, this will dominate in here. Now we have the equivalent resistance that can be calculated also using this formula, which is then approximately 6.667 kilo ohms. Now using Ohm's law, again this formula here, because we know the equivalent resistance, we know the I, capital letter I, and now we can multiply those two, and then we have the end result here, which is then shown here, which is then 10.23 microvolts RMS. And again, the dominating part here for this part is the broadband noise current value. Okay, that's for the second part. Let's now move to the third part, which is the noise contribution at the input due to the resistors only, which is the terminal noise voltages. So to calculate using the white noise or the terminal noise formula for the resistors, in this case of course we have two resistors, but we can also take that, the equivalent value of that one, and that is again seen at this node to have the calculations much more easier. So we have then again the equivalent resistance, and then the terminal RMS noise voltage for the resistors given in general form is this one. This is a very general formula, which is then the terminal noise voltage RMS is then the square root of the 4 kTr, which is then the value of the specific resistance which you're looking for, times the noise bandwidth. Now we have of course some parameters here. The K is a Boltzmann's constant, which is given by this value in joules per Kelvin. We have the T as the absolute temperature in kelvins, and most of the time we'll just use for the operation in the circuit the room temperature, which is at 27 degrees, a little bit hot, but that's actually a really nice round number, 300 kelvins. The R is the equivalent resistance in ohms seen at the node, and we have the noise band, which is then given in hertz. So if I now use that for a specific case in this circuit, I have R, which is then R equivalent, which is then 6.667 kilo ohms, and the noise bandwidth was 9.425 megahertz. Now if I now substitute the values for the circuit and also the Boltzmann's constant and also the temperature, I have then this expression. This will be then 32.50 microvolts RMS. So I have now also the contribution by the resistors. This is the contribution of the resistors. So the total input referred RMS noise voltage can now be calculated, because now we have the necessary elements for the input referred RMS noise voltage. So the input referred RMS noise voltage is then calculated using the root sum of squares. We already know that, which is then this formula. We have discussed this earlier. Now, let's summarize what we have. We have now the noise voltage input referred RMS noise voltage due to the voltage noise source of the OpAmp. This is this value. We have also the input referred RMS noise voltage due to the noise current source of the OpAmp, which is then this value. You can see this is larger than that one. And we have the terminal noise, so that's actually the input referred RMS noise voltage due to the resistors only. And this is actually larger than these two values. Now, if you now combine these three in this formula, in here, and you do the math for yourself, you will get the input referred RMS noise voltage is 34.41 microvolt RMS. What you see here is actually the following. The green one, which was actually the contribution by the resistors, so the terminal noise, is actually dominating, because the end result, the effective value of your input referred RMS noise voltage, is close to the value of the value due to the terminal noise only. So that's most of the time also the case when, this is just a rule of thumb, when this is at least 3 times larger than the rest of the values, you can consider this will dominate, and you will just take this one for very rapid calculations. But in this case, it is a little bit accurate to take them all, and we have then 34.41 microvolts RMS. Okay, now we have the first part of our exercise, the question. And again, this is dominating, which is then the terminal noise due to the resistors. Now let's also calculate the total output referred RMS noise voltage, because this is now very easily done, because we know already what the input referred RMS noise is. We know the closed loop noise gain, which is then given by Ng is equal to 3. Now we can say input referred RMS noise voltage. We already had that, which is 34.41 microvolts RMS. And then I can say output referred RMS noise voltage is then given by this expression, which is just the noise gain times the input referred RMS noise voltage. So just substitute the value 3 times this value, 34.41 microvolts RMS. And if I do the math here, you will get 103.2 microvolts RMS. That's what you get at the output, and this is then the result. So we will have an input referred RMS noise voltage, and this is the output referred RMS noise voltage. Of course, multiplied by 3, you will get from there to here. Okay, that's actually the result here for 3 separate cases for the input, and also then the total for the input referred RMS noise voltage and then the output referred RMS noise voltage. Of course, we need to verify this in the simulation, so let's look at the simulations also. But before we move on, let's also check the noise, signal to noise ratio SNR, which is a very important parameter. Now, let's summarize this very quickly in briefly form. The signal to noise ratio SNR is a measure that compares the desired signal level to the noise level. And if you make it a little bit more specific, the SNR is defined as a ratio of the signal power to the noise power. And it is often expressed in decibels, so in dBs for short. Now, a ratio larger than 1, higher than 1, indicates that you have more signal than noise. And if you have, of course, a ratio which is larger than 1, that means greater than 0 dB. And if you have a ratio which is then between 0 and 1, which is actually attenuation in terms of the signal to noise ratio, then you have less signal than noise, or you have more noise than signal, which is of course not what we want. We would like to increase the signal to noise ratio, actually make it as large as possible. Now for the circuit, the SNR at the output for a specific frequency can be calculated using this expression. And I say specific frequency because it has some dependency of the frequency, but it will settle down to some value, and we will see that also in the simulation results. So this is the formula. You can see that SNR is 20 log, again already given in the dBs, 1 over that output referred RMS noise voltage, and we already had that. So if you now substitute that in here, you will have approximately 80 dB. So it is a little bit closer to that one, 79.73 dBs. And we will check this in the simulations also. But before we move on to the SNR simulations, let's first start with the frequency response and specifically the bandwidth. This is the result of that plot. So this is the gain and this is the frequency, and we have again our circuit here for reference. What you see is actually the DC gain here. We have the cutoff frequency, and we have some labels here to emphasize that we have the required model for our circuit. Now what you see is the DC gain is 6.021 dBs, which is, if you do the math here, going from the dBs to a scalar value, which is then 2. And we had the signal gain of 2, because, of course, in magnitude, it is minus 2, but we only look at the gain here, and if you also plot the phase of this, you will see it will be a minus 180 degrees for very low frequencies. So the DC gain is 2 as a scalar value, so that is confirmed with the calculations and also the simulations. The cutoff frequency you have calculated using the signal bandwidth, and that was then gain bandwidth product over noise gain. That was 6 megahertz, and we see this exactly here also in our calculations, and I mean in the simulations. We also had an assumption that our system will behave as a first order system, and then specifically a first order low pass filter. But we need to of course check that. How can we check this? Now let's look at the labels here. We have several labels. We have 20 megahertz here, and it has a value of the gain is minus 4.85 approximately. If I go 1 decade above with my frequency, so I will make this 10 times larger, it will be then 200 megahertz. I need a decrease of 20 dBs. Is this correct? Let's check that. So this is now minus 4.85 dBs, and I need actually minus 24.85, which is very close, not really precise. So it is very close to that one. I can also check that for this one, because maybe this is already in that shape, which is not really as slow, which is a constant. So let's also look at 60 hertz and 600 megahertz. So that's also a decade. So which is then here minus 14.06, dBs at 60 megahertz. And if I go 1 decade up in my frequency, so 10 times larger in frequency, I will need, of course, decrease by 20 dB. That means actually minus 34.06 dB, and which is then, this is almost minus 34 dBs, and that is also very close to that decrease of 20 dB. So you can see, looking at these labels, that the first order approximation and also for the low pass filter is valid, since the decrease in the gain is very close to 20 dB for each increase of 1 decade in the frequency. So that is a confirmation, and we also know that the cutoff frequency is correct, 6 megahertz, and also the signal gain for the DC gain for the circuit. So that is all confirmed in the simulations. Now let's also look at the input noise voltage spectral density. And again, we see that the shape of the input noise voltage spectral density has the 1/f noise part, and also the part which is then constant. So that's also confirmed here. You can see the frequency dependent part is the 1/f noise, which is this part. And then at some point, let's say at 1 kilohertz, you can see it starts to level off and it doesn't change its value. So we have then the frequency independent part, which is then the broadband or the white noise part. Okay, we have also the output noise voltage spectral density, which is of course the multiplied part of the input noise spectral density. Then you will have this curve again. We have the first part, which is 1/f noise, and then we have the constant part, which is in the broadband region. But the important thing here is that the broadband region doesn't stay actually constant for all frequencies, but it will go down and then approach zero value. Why? Because for calculations or the simulations of this OpAmp for the input, you don't actually take into account the frequency limiting of the OpAmp, so you only look at the input. For the output, of course, you go through your OpAmp, and that will of course cause that frequency limiting or the bandwidth limiting of the OpAmp, and that will of course then reduce that gain because the bandwidth limitation of the OpAmp, because we had a cutoff frequency of 6 megahertz. So you can see at this level you have some value for your output noise spectral density, but at the cutoff frequency it will of course then get lower by a factor of square root of 2, and then it will decrease again and then approach a value which is then almost zero. That's why we have the zero here almost at the output and not at the input, because of frequency limiting of the OpAmp. So again, the frequency dependent part is the 1/f noise. We have the frequency independent part, which is the broadband noise or the white noise part, but the output noise goes to zero due to the bandwidth limiting of the OpAmp. Okay, let's also look at the total RMS noise voltage at the output. This is again the plot and also the circuit for the future reference. You can see the output RMS noise voltage will start very low, and if you integrate it over the frequency at up to 1 gigahertz, for example, then you can see that the blue line will increase and then settles down at approximately 103.01 microvolts at 1 gigahertz. Now we had calculated it was 103.2 microvolts RMS, which is very close to that one, because the simulation is this and the calculation is that. So I can see this is really close to what we have calculated, so that's also a confirmation in the simulation. Let's also look at the signal to noise ratio, the SNR. Again, it starts in this case very large, 181 dB approximately, so this is the signal to noise ratio in dBs. This is the frequency, and it will then decrease rapidly and then have some constant slope in the log scale, and then also settles down to a value which is here 79.74 dBs. Now we had this formula for the SNR and calculated using the output RMS noise voltage, and we had this value 79.73 dBs, and that is the calculated value, but the simulated value is 79.74 dBs. So you can see it is very, very close to what we have calculated. It's actually very nice results. So the calculation and also the simulations do match very well in the SNR results. So this is all what we have determined in the simulation in the SPICE, and also verified this, and our calculations do match very well. That's actually a very nice result. We will now also see that in the actual simulator, so you can see how I did the plots, and you can also generate that by yourself using maybe a different simulation program. So let's jump to the SPICE simulator. So we are at our simulation. This is the simulation circuit. So we have the OpAmp OP209, the power supplies and the feedback resistance, and also the input resistance, and we have the noise current source and noise voltage source of the OpAmp model. If I double click on that one, which is actually provided by the this simulation software, which is the TI SPICE, which is then given the sources here are provided by the Texas Instruments. So if I now double click on that one and I go to enter macros, you can see there are some values which are shown here. So this is specifically for the noise current source. You can see that it's 20 nanovolts here per root hertz for the 1/f part, and evaluated at 0.1 hertz, which is actually what we had also in our plot. And it has a broadband noise value of 2.2 nanovolts RMS, I mean per root hertz. So that's actually, these three values are actually what you need to substitute in this macro model. That is what we have for the source noise voltage. So let's close this netlist and look also at the macro for the noise current, and also enter the macro. You can see again, this is given now here in femto amps, so it is now 3.750 pico amps, or 3750 femto amps. And this is a value for the 1/f noise current evaluated 0.1 hertz. That's also what we had in our plot and also used in our calculations. And this value was 500 femto amps for our broadband noise current. So again, you see the three values in our macro model. And of course there are some formulas here which is not in the plot at the moment, but that will allow you to use the model and generate the required results. So I will again close this. I just then show you what we can do using this two sources provided by the Texas Instrument in this case for this TI SPICE simulation program, and then generate the plot for the noise. So this is just an AC input source. It doesn't have to be a sine, it can be anything. It can be also a triangle, which you prefer, just an AC signal. And we have an output to measure the output noise also. So let's look at an analysis. I'm going to noise analysis and start at a specific frequency, let's say 0.1, and then all the way to 1 megahertz. And this is the number of points to have the accurate measurement. So I've found out that this is actually what you can get at max. And I have now several plots here. So you can take the output noise, which is actually the output noise spectral density, input noise, which is then the input noise spectral density, total noise, which is then actually the total noise at the output RMS, and this is then the signal to noise ratio. So let's click all of them and then generate the plots. Okay, this will run and will generate the 4 plots for us. Let's increase this. This is the output, so the output noise spectral density, and this is the frequency, and this is the value of that output noise spectral density. You can see it has a 1/f noise part, it has the broadband region, and also the value which then levels off due to that band limiting. You can see it has a value approximately 33.7 nano volts RMS, I mean per root hertz. But if you go down in the frequency, let's say it has to be of course at 6 megahertz, then this ratio is then has a ratio of square root of 2. So we can calculate this. Just do the math for yourself and check this that this is indeed lowering by square root of 2. And that will of course go down, down, down all the way to 0 approximately. So you can already see this is picos. Okay. Let's also look at the input. This is an input noise spectral density. You can see it is also one of ref noise part and also the broadband part, but it's, of course, it stays the same because there is no band limiting at the input. It can of course happen that you have a capacitor at the input, then of course that will, or an inductor that will of course have some band limiting, but it is of course now independent of the bandwidth limitation of the op-amp, so it is just a one-off ref noise part and also the broadband part. Okay, let's look at the the total noise, which is then the total noise at the output, RMS. You can see that it starts off very small, so I will label this. You can see at 0.1 Hertz, it's actually just 0, and it increases. You can see the label, it increases, now it has a value of, let's say, 7.88 microvolts RMS at approximately 55 kilohertz, and if I now move on, it will increase and increase rapidly, and then settles down actually to a value which is here 103.01 microvolts RMS. That's actually what we also have seen in the discussion previously. Okay, that's for the total noise voltage RMS at the output. Now let's all look at the signal noise ratio. You can see the signal noise ratio starts off very large, goes down and has some slope in the log scale which is constant, and then also settles down to a value which is then 79.74. Again, let's label this to check this also in the label, and you can see that the label also confirms that value which is then very close to this one. Of course, this will approach when you go to very large values. Alright, this is then for this example, again confirmed with our calculation and all simulation, and you've seen also how to generate these plots in the SPICE simulation program. So this is done for our second example of the op-amp circuit, in this case specifically the inverting amplifier, and we have provided you the plots for specific parts for the output, for the input, spectral density, total RMS noise voltage at the output, and also the signal noise ratio. Alright, that was for example number 2. If you have any questions or comments, please let me know and I will try to answer them as soon as possible. Thanks again for your time, and I hope this again clarifies the situation in more detail for the different circuits. Don't forget to like and share, of course, such that we can reach more people for this very interesting topic. And see you next time. Take care.